Deep beneath the Gobi Desert, near an isolated city called Wuwei, engineers just did something no reactor on Earth had pulled off before. They took a rock that cannot sustain a nuclear chain reaction on its own and turned it into one, while the reactor kept running. A handful of that rock holds the same energy as 3.5 million tons of coal, not a truckload, a handful. And China just spent a year mapping how much of it is actually sitting in its own soil. Inside that reactor, engineers are cooking an inert stone directly into usable nuclear fuel. No refinery, no enrichment plant, just a stream of neutrons and about a month of waiting. Watch the screen, not just the words. That element is about to rewrite its own identity 3 times before it's finished. For 60 years, Western regulators called this chemistry too corrosive, too unstable to run outside a laboratory. Beijing just quietly flipped the switch anyway. And the blueprint sitting under that desert doesn't just solve China's own fuel problem. It threatens to gut the leverage of every country that built an empire selling uranium to the rest of the world. Uranium became king for one reason. It is violently lazy. Split one atom, and it instantly explodes into a chain reaction with zero effort. No waiting, no decay chain, no patience required. By the 1970s, this instant gratification had built a $1 trillion industrial empire: enrichment plants, fuel rod factories, a supply chain refined across 5 decades until uranium became the only fuel anyone in Beijing trusted enough to bet an entire grid on. But Cold War generals didn't want clean electricity. They wanted a byproduct called plutonium-239, the raw material for nuclear warheads. Uranium didn't win because it was better. It won because it was a weapon disguised as a power plant. Thorium walks in wearing the opposite disguise. Call it the anti-bomb element. Breed it into fuel, and it arrives contaminated with a stubborn isotope that floods out gamma radiation strong enough to fry warhead electronics, and strong enough for a satellite to spot from orbit. Nobody could smuggle that into a weapons program, so nobody funded it. America actually built one anyway. At Oak Ridge National Laboratory, a working molten salt reactor ran for 4 straight years, starting in 1965. Real fuel, real heat, real proof the chemistry worked. Then, in 1969, Washington deliberately pulled the plug. 5 decades of revolution got buried in a government archive, leaving the door wide open for China 50 years later. Which brings the story back to today. China now runs 63 large reactors, and every one of them still needs a foreign hand near its own power switch uranium, shipped in from Kazakhstan, Australia, Canada, countries Beijing doesn't control and can't fully predict. A war, an export ban, a blockade anywhere along that chain, and the lights start to flicker at home. Forget refueling trucks. Forget shutting the plant down for weeks. Engineers in Shanghai figured out how to feed raw thorium straight into a reactor running at 700 degrees Celsius at full power without stopping a single pump. The reactor never blinks. It just keeps eating. This project moved at a pace that stunned outside observers. China's Science Academy greenlit the budget in 2011. Ground broke in 2018. By 2021, the reactor was already finished 3 full years ahead of its own schedule, while most of the world was still arguing over whether this chemistry was worth funding at all. Then the pace kept accelerating. Critical within 2 years of breaking ground, full power within months after that. And then, without ever pausing the reaction, engineers started pumping fresh fuel into the loop, something no molten salt reactor on the planet had ever managed outside a research paper. November Sarist, Duani Lime. Shanghai's engineers confirmed it. That inert rock from the opening of this video had transformed itself. Live. Inside the reactor, the salt stream was quietly printing its own nuclear fuel from scratch, and physics had nowhere left to hide. The breeding cycle wasn't theory anymore. It was running. 60 years after Washington buried the paperwork, a single institute in Shanghai just finished the sentence America started. And a reactor that manufactures its own fuel out of ordinary sand raises a much bigger question. What happens to every uranium mine on the planet once nobody needs to dig anymore? Every uranium reactor on Earth fights the same enemy: pressure. Water superheated past 300 degrees needs a vessel rated for 150 atmospheres just to stay liquid. This reactor skips that fight entirely. The physics of a pressure explosion simply do not exist here. Molten fluoride salt, stays liquid past 1200 degrees at ordinary atmospheric pressure. No pressure to contain means nothing left to explode. Not unlikely, not well managed, just physically off the table. If the core overheats anyway, it doesn't wait for a human decision. It starves itself. Heat thins the fuel automatically, and thinner fuel simply can't sustain the same reaction. The hotter it gets, the harder it slams its own brakes. The real insurance sits at the bottom of the vessel. A plug of frozen salt, kept solid by a small fan running around the clock. Lose power, lose the fan, and that plug melts on its own within minutes. No panic in the control room, no operator decisions. Just fundamental physics stepping in. When power fails, the fuel falls straight down into tanks built to swallow it and kill the reaction cold. None of this survives without a metal built to withstand what amounts to a nuclear acid. Hot fluoride salt strips chromium straight out of ordinary steel, cracking it from the inside. Shanghai's nickel-molybdenum alloy shrugs that off, corroding at a rate measured in micrometers per decade. Even that alloy has one saboteur to guard against: radioactive tellurium, born from the reactor's own fission, that creeps into the metal from inside and turns it brittle. Engineers caught the saboteur early and trapped it in the salt chemistry before it ever reached the wall. Shanghai didn't just build a safer reactor. They built a machine that's nearly immune to the kind of disaster that made the word Fukushima famous. Shanghai isn't stopping at 2 megawatts. The next reactor on the roadmap is 5 times bigger, 10 megawatts, targeted for around 2029. And this one won't just make heat. It will spin a turbine and put real electricity on the grid for the first time. The turbine itself is its own quiet breakthrough, a closed loop spinning on compressed carbon dioxide instead of steam, squeezing more electricity out of every degree of heat while needing no river or ocean nearby to cool it. Park it in a desert, and it just works. Western labs took notice. After decades of near-total silence, American molten salt startups suddenly found funding again, and international nuclear regulators started quietly requesting site visits to a reactor most of them had written off as a curiosity 3 years earlier. Not everyone is convinced the pace holds. Nuclear projects have a long, expensive history of slipping their own deadlines, and a 10-megawatt demonstration is still a long way from powering a city. The next 4 years will decide whether this becomes an industry or just an impressive footnote. Here's the part the highlight reel skips. That reactor under the Gobi produces 2 megawatts of heat, barely enough to warm a few hundred homes. A commercial power plant needs 50 times that output, and China's own roadmap doesn't target one until sometime between 2035 and 2040. That gap between a lab demonstration and a national power grid has swallowed entire technologies before. Fusion has promised commercial power for 70 years running. Nothing about a working 2-megawatt reactor guarantees the 400-megawatt version ever gets built on schedule. Running a reactor this novel also means training an entire workforce that doesn't exist yet: operators, inspectors, technicians who understand a chemistry almost nobody outside one institute has ever handled. Every major nuclear build-out in history has been slowed by exactly this bottleneck. Not the physics. The tellurium cracking problem from Act 4 isn't fully solved, it's managed. Nobody has run this alloy for the 30 or 40 years a commercial plant actually needs, so nobody can promise it survives that long. Real long-term durability data simply doesn't exist yet, because the clock has barely started. Recycling the spent salt is its own unsolved puzzle. It requires vacuum distillation, chemical separation, and electroplating equipment that has to be swapped out by remote-controlled robots, because the salt stays lethally radioactive. Nobody has run that recycling loop at industrial scale even once. And the anti-bomb radiation from Act 2 cuts both ways. It kept thorium out of weapons labs for 60 years, but it also means every gram of this fuel has to be handled behind heavy shielding, which quietly adds cost and complexity nobody puts in the press release. None of that makes this a failure. It makes it a 15-year construction project pretending to be a finished product on the news. And in a race where the only thing that matters is who finishes first, being 15 years from commercial power might still be 15 years ahead of everyone else on Earth. While regulators argue about grid-scale timelines, Chinese shipbuilders already found a shortcut around the whole problem: skip the grid entirely and bolt this reactor straight onto a ship. In 2023, at a shipping expo in Shanghai, State shipbuilders unveiled the design for a container ship carrying 24,000 boxes, among the largest cargo vessels ever conceived, powered not by bunker fuel, but by a 200-megawatt thorium reactor sealed inside its hull. Call it a nuclear battery, not a power plant. The entire reactor sits inside one sealed module that never needs opening at sea. It runs for 15 to 25 years straight. Then the ship simply sails home, and a crane lifts the spent module out and drops a fresh one in. No refueling stops, no dependence on bunker fuel prices that swing with every war in the Middle East. A ship like this could circle the globe for 2 decades without ever needing to touch a fuel dock, and every port it skips is a choke point it no longer has to fear. By late 2025, the same shipyard confirmed it's already refining a follow-up design, a 35,000-ton class vessel carrying 25,000 containers, with construction targeted to begin around 2035. The nuclear battery isn't a concept anymore. It's a production roadmap with a start date. While engineers were solving corrosion problems in a lab, geologists were quietly solving a different problem outside. In early 2025, a national survey mapped 233 separate thorium-rich zones across Chinese territory, the first time anyone had actually counted. One site did most of the heavy lifting. A rare earth deposit in Inner Mongolia, already known for decades, now confirmed to be sitting on roughly 1 million tons of thorium sitting there the entire time, mistaken for industrial leftovers. That number is a survey estimate, not an audited reserve worth flagging, honestly. But even treated conservatively, it points to enough thorium sitting in Chinese soil to matter for centuries of energy planning, not just one demonstration reactor. And here's the part that turns geology into a monopoly. Thorium doesn't need its own mines. It rides along for free inside the rare earth ore China already refines at massive scale, which means China can recover it at close to zero marginal cost, while everyone else has to pay just to bury it as waste. That single fact locks in a supply chain nobody else can easily copy. Reactors need thorium. China already controls 60 to 80% of the rare earth refining that produces it as a side effect. Building a rival supply chain from scratch means building an entire rare earth industry first. The next move is already public. Beijing plans to export small modular thorium reactors through its Belt and Road network to India, Turkey, Egypt, Brazil, countries with real thorium deposits of their own, but none of the 2 decades of engineering knowledge it took to actually run one. The same playbook applies at sea. Every one of those thorium-powered container ships still needs Chinese-trained crews, Chinese-built replacement modules, and a return trip to a Chinese port for every swap. Land or ocean, the dependency runs through the same address. Sell the reactor, and you don't just sell hardware. You sell dependency spare parts, trained technicians, decades of maintenance contracts, all flowing back through Shanghai. The uranium cartel America once relied on has a thorium successor now, and it isn't headquartered in the West. So the question this leaves behind isn't whether the physics works. Shanghai already proved that on the 1st of November 2025. The real question is what happens to the rest of the world's energy order, its power grids, its supply chains, even the ships crossing its oceans once the country that spent decades importing uranium starts exporting the technology that replaces it entirely.